Dr. Rituparna completed her PhD from IIT Guwahati in 2023. She served as assistant professor at SRM University, Andhra Pradesh before joining IIIT Bangalore. Her research focuses on design of low complexity machine learning and deep learning algorithms and their efficient implementation on FPGA or ASIC. Her research also includes design and implementation of ML algorithms for biomedical applications. She designed two hybrid low complexity decision tree algorithms and implemented the training accelerators on FPGA and ASIC during her PhD. Today, she is going to talk on design and implementation of low complexity decision tree algorithms on FPGA and ASIC. So please welcome to them.
So good afternoon, everyone. So thank you for the introduction. So today I will be presenting my PhD research mostly, because after PhD research is still now under preparation and under review. So I have designed two decision tree algorithms, low complexity, because when we are talking about FPGA or ASIC, we have limited resources on board, on chip available. So we have to utilize those resources, and we have to minimize the utilization and consumption. So I have designed the low complexity decision tree algorithms, and I have implemented their training on FPGA or ASIC. So this is the content slide. I will not be going into details, so some slides I will be skipping. So I will discuss basically two algorithms, and third one only classification I will discuss. And I will another architecture, means two architectures of one algorithm, and another algorithm, this HDT, and this one I will only discuss the classification. So to start with, what is a decision tree structure? This is a very simple algorithm in machine learning. So what happens here is that, unlike the neural networks, where there are so many layers, there are so many computations involved, and according to that, our resources also increases. But in decision tree, the structure is quite simple. We have a root node where we start. We enter through one node there, and based on what tree you are designing, either binary or more, if you want more splits, then it will be multi-split decision tree. So my research was specifically on binary split. That is, one node is splitted into two child nodes, and like this we go till certain depth. So we test certain conditions, and if those conditions are satisfied, we stop at that depth, and we don't go further. We don't split the nodes further. So what happens? We have split nodes till before the last step, and in the last step we have our leaf nodes where the decision is stored. There is no more testing, no more conditions there. There only we store the decision. Let us say I am predicting whether the information that I have got is a female or from a male. So we will test certain conditions, and based on those conditions we will arrive at a decision that yes, he or she is a male, or he or she is a female. So like that, decision tree is a classification algorithm basically. So why I have chosen decision tree during this for implementation on FPGA? One criteria of decision tree is a top-down approach, that we start from the top and we go down splitting the nodes, and we go down the level from top to bottom. And so we can easily interpret the design. There we can just look at the design. We can tell that node is this condition is there in the node, and this is a split node, and then we can tell that this is in the last node what we have is a decision node, that is leaf node. Then another condition is low complexity, that I have already discussed. And the main reason for choosing the decision tree is the hybrid structure. That is, the condition that you put in this node is not fixed. You can put any condition in the node. So you must be knowing about neural trees. So these neural trees come from the node being one neuron. being a neuron. So this tree is a very hybrid one. You can put any algorithm or any condition in the nodes and you can get a hybrid structure. So one reason for using this decision tree was this reason also. The structure is not at all fixed. You can change the algorithms inside the node and you can it will result into hybrid algorithms, right? So some work has been done on classification, implementation of decision tree on FPGA. So some people implemented serial architectures for data filtering, sensor data filtering from some aerospace projects like that. And some people have also used pipeline, serial architecture, pipeline architecture of conventional decision trees, that is C4.5, CART, then IDE, ID3, those algorithms are there that they have implemented only the classification. Because of the high complexity, they could not implement the training, but one work is there, which this one, he implemented the training on FPGA. But what he did was he used high level synthesis, due to which he required multiple FPGAs. 5 FPGAs he needed to implement this training of CART. CART is classification and regression tree. So there are many complex calculations are there, like sorting is there, then impurity calculations for each sorted value. So those things increases the complexity and is also takes more computational resources. So that is the reason that I modulated the this conventional algorithms, and I have implemented a low complexity where the calculations are reduced so that lower resources are used on board. Because training is the slowest phase, because there is huge data involved in training. When you are training a machine learning algorithm, at least for the smallest data set that I took, at least 100 to 150 instances you require to train. So those type of that requires high memory also, and then again calculations are more in training phase, so it increases the complexity. Which, and if you don't implement the training on device, then what happens? If you have trained for some application, then you have to again go back and train for some other applications in software, and you have to implement it on hardware, come back to hardware. But if you implement the training on board itself, then what you can do is you can just change the training data, load the training data, you can train the device, the circuit is already there on board, and you can use it for classification. That's why that was the reason that, behind implementing the training. So after implementing the training on FPGA, the advantages that I got was the acceleration, execution was very much accelerated, that I will show in my results, compared to Python, compared to C, and compared to other existing accelerators that are available. Compared to all those things, this acceleration is accelerated, execution is accelerated, and also if you implement a low complexity algorithm, then the hardware that you will get, it will be resource as well as cost efficient. Resource efficient means you will use less power, which will be more applicable for biomedical applications, where that chip might be embedded in your body, so it should take less power so that it goes for a longer time. And this reconfigurability of FPGA also allows for easy retraining. So reconfigurability means there are some resources on FPGA, we can use them and we can reconfigure them according to our circuits. That is a semi-customized design. Unlike ASIC, which is a fully customized one, you cannot change the circuit once it's fabricated. So first one is the TMDT, that means two means decision tree algorithm, serial and mixed implementation. So what is two means decision tree? So this two means decision tree, what it does is in each node it stores two means. One is left mean, one is right mean. Then what we do is, based on the incoming data, we calculate the distance of the data with the both of the means. If the data is closer to right means, that means that it belongs to the right cluster. So what we do is we send it to the right child. Otherwise, if the incoming data distance is closer to the left child, that means it belongs to the left cluster. So we send it to the left child. So this is the splitting condition in the split nodes. So during training, what we do is in the first iteration, we just take the class 1 data, class 0 data, and we take a average. That's our initial mean. Now what happens as the data comes in, the distance is checked. Which one is the data is closer to which mean. According to that, the data is used to update that mean. If the data is closer to during training, if the data is closer to right mean, that means the right mean will be updated using that data instance. Otherwise, if it is closer to left mean, that is, it will be updating the left means, right? During training, we update the means of each node. Once the training is done, that means these two means stored in each node are fixed. After that, whatever instances are coming, we only check the distance, and accordingly we send the data to the next either right child or the left child node. So this goes on until some termination criteria is met. During the training, we have given some termination criteria. Based on that, we stop the further splitting of the node. So this is my termination criteria. Node input deficiency, that is the number of data coming into the node. If it is less than some parameter eta, if it is, that is, if I am for my design it was 5. If my number of data coming in for one data set, it was 5. So if it less than 5 data instances are coming to that node, means we don't need to split it further. It can be declared as a leaf node. We are not splitting, means it is declared as a leaf node where only decision is stored. There is no criteria to be checked. Another condition is this input purity, node purity. If your node purity, everyone knows, I have used here misclassification impurity. So it takes total number of instances from one class and divided by total instances coming to that node. If the purity reaches 95% or more, then I don't split that node further, because that is a almost pure node, so it can be declared as a leaf node. We don't need to split this node further. So my purity threshold was PTH. It was 95%. If the purity is greater than or equal to 95%, means your node is pure. It is a decision node. No need to split it. So this is the architecture of the serial one. So I will not go into the details. So why it is serial? Because the data is coming, the nodes are executed, trained in a serial fashion, like first node 0, then node 1, then node 2, then node 3, like that. And why it is mixed? Because here in the last step, what we are doing is, if I am if one training data has completed execution training of node 0, then I am sending this children data to node 1 and node 2. So I specified 2 steps during training, during the mean updation. First is the average we calculate for class 0 and class 1. Then in the next iteration, we pass the same data again to update those 2 means based on the distance, not on the class this time. So what happens here, what we have done is, suppose our training set completed the mean average calculation in node 0. And then I will start with the mean update, right? So once the update of node 0 is done, then we will send the data to node 1 and node 2. Now in node 1, first step will be again calculating the average of class 0 and class 1, right? So once this average is done in node 1, then we have to go for mean update. So once average calculation in node 1 is done and we are going for mean update, we will start the average calculation of node 2 in parallel. So because our average calculation resources are free, so I am giving the node 2 data in that average calculation resource, and mean update is going for node 1. Similarly, what happens once node 2 mean average calculation is done, then node 2 data is sent to the mean update unit, and again our mean average unit is free, so node 3 data is sent to, because node 1 has completed the training, that means which node data is going to node 3 and node 4, which are the child nodes of node 1, we know. So we can proceed with the average calculation in node 3. So when average calculation is node 3 is going on, at the same time we are updating the mean in node 2. So we have parallel these two operation, and but the actual calculation is serial. So that's why it is a serial and mixed, both type of implementation. So first we have this average calculation unit, and this is our critical path from data memory to the comparator. So whatever highest frequency, maximum operating frequency is a critical parameter in hardware design. So as you reduce your critical path, you get the higher frequency. So I have implemented a latch here, due to which my critical path is only from the data memory to the comparator. So I got a good frequency for this design. So after this mean update is done, it is going to the after this mean approximation, that is the averaging, is done, then we go to the mean update module. After that, split module is there, where means are decided. Now the data again comes and is splitted, whether it is going to the left child or the right child of the parent node. So that is the split module. After that, when all the nodes training is done, then we check here whether the termination condition is satisfied or not for the node. If the termination condition is satisfied, then the node is set as a leaf node. If the termination condition is not met, then it is again splitted as a then it is again splitted into child node, right? So again, after all the nodes are done here, then we again go to the pruning module, where we again check the nodes. If some nodes are having less, any one of the termination condition it is not matching, then we prune those nodes. So that is the pruning module, so that our data do not overfit. So this is the distance calculation module, Euclidean distance. So squaring and then adding. And this is the pruning module, where we compare with our the two condition, node purity and the node input threshold. We compare it these two parameters, and accordingly we set it as 0, that is split node, 1, that is leaf node. So in this design was written in Verilog HDL, and it was implemented using Vertex UltraScale Plus board, the recent board at that time. And the frequency that I got is 62 megahertz, maximum operating frequency, based on the critical path. So this is the node data separation after each node. So we can see that node 0, the data is so much mixed up. Here it is still somewhat pure, and this we can see that we have achieved almost very high purity. So here we are stopping till depth 1, depth 2, and depth 3. We are stopping here, and we were declaring these nodes as leaf nodes. So this is for this design, I tested it on 3 data sets. One is mammography, that is breast cancer data set. One is occupancy, whether the room is occupied or not, based on some input data, it will decide. And another is skin, that is from a photo, which are the skin pixels, which are the non-skin pixels, those will be detected. So as we can see here that my algorithm accuracy was little low for small data sets. This is a small one, this is a medium one, and this is a big data set. This only consisted around I think 197 total data. So 80% used for training and 20% for classification, and occupancy around 12,000 instances, and skin dataset around 56 or 54 data instances. So this was my largest dataset. So we can see that the accuracy almost was equal to C4.5 training. This comparison was done on Python. I implemented the algorithm first on Python, then I saw how many nodes we require. After that, it was implemented on hardware. So this training time, we can see that there is a huge latency gap between TMDT and C4.5. So this latency for FPGA was very much less, and for Python was very much high. So we got almost, for this large data sets, it performed good, where we got almost same accuracy, and the training time was also reduced to a great extent. So at that time, there was not much resource publications to compare to. So I compared with this one, that Chrysos one. So I got latency also less for all the data sets, and also number of FPGAs were reduced, although I used less number of features. So it will increase somewhat the resources, but latency will be same. And I could support 2 classes, while this proposed one could support 16 classes. So resource utilization comparison I have done with classification accelerators, as that paper did not report any resource usage. So here you can see that as it is the classification, so this the LUT usage is less in their case, while I have used more LUT in my case because computations were more, and but flip-flop it was reduced, and BRAM was also reduced. BRAM is the random access memory that was used to store my training data, and my data points were also more compared to the proposed existing ones, and this used conventional k-means, and this was their work only, but they optimized the k-means algorithm and implemented it on FPGA, only the classification. So this was the resource consumption of my design. So maximum resource was consumed by logic and also the switching of the signals. This is power consumption, not resource. So switching signals consumed the higher amount of power, and logic, others were very less, other percentage. So now that TMDT only I also implemented using pipeline one. Here what I did was, earlier I pipeline the average calculation and the mean update unit. Now here what I did is I pipeline the node calculation. So what happened is, this is my initialization module. I used node 0 mean calculation, and then I went to this update module, right? So what happened is what happened here is, this child splitting was done in parallel. Like when I was doing this node 1 splitting, that data set whatever is coming into node 0, I was sending to node 1 and node 2. At that same time I was calculating the average. I was not giving extra module for that one. In parallel only, whenever I was sending the data, I was calculating the initial mean, and then when I got to that node, I calculated the updated mean using the update equation. Other things in the algorithm, it was similar. So this was the architecture for this pipeline one, where I had two stages of pipeline. Here the node 0, that is the parent node, mean update was going on, and here I was in the pipeline stage 1, I was processing the next two nodes, right, whenever the data was coming according to that. So here also I used distance calculators because the algorithm was same. So based on the distance, I was sending the data either to the left child or right child. And here another modification that was done was, this multiplication was replaced by shifting operation. I was not using any multiplication. So I did this alpha was taken 0.81 or something, where if you shift by 3 places, then you get the multiplication of alpha. So this multiplier operator was also replaced. So this is the timing cycle, that in same time I was processing 3 nodes. So this was the experimental setup where I loaded the training data into on-chip memory. Then I used to train it in the training hardware. Now the problem here was, I could not go beyond 54,000 of data instances, because it would not allow more than that to be stored in that memory. So in the next proposal, I solved that problem. But before that, here the frequency also increased because of the pipelining, and because 3 nodes were done in executed in parallel, so my speed also increased in the same board. So I have compared it with my previous design. Latency also decreased for the same data sets. I have given this table. Similarly, this resource consumption was also a bit higher because 3 nodes now were executed in parallel. Huh? DSP, that multiplication. Some multiplication I replaced with shifting, but still there were some. So it is reduced, but still it is there. Digital signal processing units, those are IPs there. So now this is the power consumption. There was not much improvement in this respect. So now next, what I did was I switched to batch mode training, where I was not loading the entire batch at a time. I loaded small batches of training data for training, and then while one batch was being executed, I pipelined the reading of next batch into the memory. So there one pipelining was done. So when one batch of data is in pipeline stage 2, what I did is I executed the next batch of data in this pipeline stage 1, and in another pipeline, what I did, this data reading into the data RAM, because here I had one register where this batch I+1 was stored, and batch I+2 started to be read into that data RAM, because now I don't need data RAM, I have a memory in between already. So here my memory consumption was reduced, and also the I could take more instances of training data. So there was no limitation on number of training data instances. It was one improvement. And this is the node architecture. So in the pipeline, what happened in pipeline stage 2, what happened, we had this mean update calculation, and in the splitting we shifted it to stage 2. So whenever one node was doing the mean update, then another node was splitting the data, and similarly next batch was being loaded into the RAM. So this is the stage 1 architecture. Node selector means which node it should go to, which node it was assigned to during splitting from the parent node. The node data was stored here, and node number was stored here, corresponding to each data. So according to the node number, this node selector selected the node module, and in that we process the data. In this stage 1. In stage 2, okay, this was stage 1 architecture. In stage 2, what we did is this splitting we did according to the node, whichever node was selected, the data was assigned to that node module, and then we assigned to the next child node of that node. Node 3 to node 6, next child node, whatever was there, it was assigned to that. So the multiplier here, what I have done is I have pipelined the multiplier also, so that I had level 1 and level 2 pipeline in the multiplication also. So we can see that A into B in digital can be done by using, if B is 0, then that corresponding to B0 bit, your output will be 0. So what we are doing is Y0, Y1 is each layer output. So in the multiplexer, we are checking if A is 0, then we are directly sending this 0 to the output. Sorry, if B is 0, we are directly sending 0 to the output. If B is 1, then we are directly sending A to the output. This is the level 1. In the next level, what we are doing is, first one, A0 is directly written, right? A0 into B0. In next pipeline of multiplication, what we have to do is B0 into A1 plus B0 into B1 into A1 plus B1 into A0. So like that, if you divide the multiplication, so in my case, the data was 32-bit. So I required 5 levels of pipelining. So this multiplier speed was also improved due to pipelining, and my final product was 64 bits, because 32 cross 32 for greater precision, I'm taking 64 bits. So now this was also done using Verilog HDL, and my frequency was 62 megahertz. So but this design could support more data sets. Earlier, I used only 54,000 instances of my skin data set, but now here I have used 100K data set. So main aim was here to mitigate the training data instances restriction. So here I have done this small data set, that is 1K. This is not 1K, I think it was 192. So, and occupancy, this is 10K, and this is skin data. I took the whole one, that is now 100K data set. So due to batch training, I am giving these batches multiple times in epochs. So my accuracy also improved. due to this batch training, but still it was less, as I got only 70% accuracy. Highest accuracy, this one was this one was lowest accuracy for this memography dataset. This lowest accuracy was compared with the accuracy of other datasets. Their accuracy was also lowest one, 67%. So another design was also there who implemented my TMDT algorithm mixed with some other one, but it was not included during my PhD thesis. That's why it's not there. So I think it will come up in the next slides. So these are my 3 designs, and these are the okay, this 12 one. This 12, what he did was he used my TMDT mixed with some other, and he proposed both ASIC and FPGA. So I have compared with that one, and these 3 are my designs. Now this algorithm, because in 2 means DT, what was happening was that when we had a noisy data, the means were seriously perturbed, and we were not getting good accuracy there for biomedical datasets. And also biomedical datasets, the data instances are less. So what happens is that with lesser data instances, TMDT performance was very poor. So what we did was we implemented a hybrid node decision tree. So in the first level, first 2-3 levels, we kept the mean dependent nodes. In the next level, we kept nodes similar to that of conventional DT, where splitting is done, and for each splits, the impurity is checked. But our splitting was different than the conventional one, because in the conventional one, what they do is they do the sorting, and then they took each instances. Let us say I have 3 data instances. Otherwise, let us assume that I have a data set where I have 2 features. One is age, one is expenditure. And in conventional DT, what we have to do, we have to sort it in a increasing or decreasing one. Let us say my expenditure from 1 rupee to 100 rupee, I have to sort it, and my age also I have to sort from lowest to highest. Then each point I will take it as a split, and I will check the impurity conditions. So if I take, let us say, age 0, 1, 2, 3, 4, and expenditure I take, so age cannot be 0, but let us assume that for now. So what the data set is not actually like this. We have to sort it in conventional DT. Then what we do is we take, let us say this is one split, and we check the impurity. Let us say this is class 1, this is class 0, 0, 1, 0. So accordingly, we will get the impurity. First one is pure, and next one will be 1/4, right? So we will take this split, then this again, this 2 in 1 split, this 3 in 1 split. So like that, we have to take as many data instances are there, that many splits we have to take, and we have to take the impurity, whichever is minimum, that split we have to take. So here, what we did is we took the range of the input data. Let us say our age is ranging from 0 to 4. So we took this range, minimum and maximum, and after that what we did was we had some form theta and j. What is this theta? This theta is the let us say you are taking this dimension, right? Age 0, 1, 2, 3, 4. Let us say you have taken this split. This split means age greater than 0 will go to left node, age less than or equal to 0 will go to right node. So 0 is your theta, and j is your this dimension number. Let us say this is dimension 0, this is dimension 1. So j0 and theta equal to 0 will be stored in the node as the split condition. Now, instead of taking this value as theta, what we did is we took the range and we divided the range. Let us say I want 3 values in a range, probable values, and we are taking those 3 as the candidate splits. And those candidate splits, we are checking whether we are getting good impurity for which split. So let us say 0 to 4, we are having, our range will be 4. 4 minus 0 divided by some criteria was there. Let us say I want 5 values. So divided by 5 into some n, and according to that, we got some say 4, 5 thetas. So from 4, 5 thetas, we tested the split for, let us say, if I take theta 1.5, then this will be coming this side, this will be coming that side. What is the impurity? Then let us say my another candidate value is 3.5. Then we will check what is the impurity. So like that, we checked impurity for 4 to 5 values, and whichever theta gave us the minimum impurity, we took that theta. In this way, what happened was, I did not need to take this many splits as number of data instances. Otherwise, I would have to take 100K splits. Another thing was the impurity calculation also I have to do for all the splits. But here only I took 5 splits and 5 impurity calculations along each dimension. Now, similarly, along other dimension also we have to take. And after that, once we specify the theta along each dimension, then what we will do among all the dimension, which theta is giving us improved purity, that theta we will take, and that dimension number we will take as our split condition. So this is theta, and this is what J is. These two were our splitting conditions of the data. Whenever the data came in, we tested its jth value, jth feature value, as against this theta value. If it is greater than theta, it will go to right child, and if it is less than theta, it will go to left child, like that. So here computation was little increased, but we got good accuracy, and the computation was less than the conventional DT. So conventional DT, we had to sort along all dimensions, and this many number of n is the total number of training data instances, m is the number of features. So these were number of impurity calculations, and which resulted in higher complexity and latency. So in my case, there was no sorting. Impurity calculations were k cross m. K is my number of candidate theta values, and m is my features, which resulted in lower complexity, and so latency was also low, but accuracy increased as compared to the previous one. Still, it was slightly low as compared to the conventional DTs. So this is how the algorithm worked. So up to DMD, that is my mean dependent depth, the nodes were similar to that of 2 means decision tree, and after that depth, I kept this splitting axis aligned splits. That is, this theta and j were stored, and they were trained using this theta and j were decided from the training data. And after that, whenever the data came, its jth dimension value was checked against this theta j, and based on that, it was sent to left child or otherwise right child. So this was my mean update equation, similar to the previous one. Here the small modification was done, that 1 minus earlier what I was doing was alpha into mu plus x I was doing. So there was some problem and more complexity was there. So once I stored this 1 minus alpha value in the memory, and this alpha value was also there, so this reduced my computations here. So this was the calculation for the range, how to calculate the range and how to calculate the theta values. So Rmax is the maximum range in that feature, and Rmean is the maximum range, minimum range for that feature. K is the number of theta values that we required. Actually, we took the middle point, then we divided it to take the number of candidate values. And then we tested the impurity like the conventional DTs. Maximum drop of impurity, we took that theta from parent to child. Let us say this is my, after splitting, this is the impurity of left child, this is the impurity of right child. So I maximize this impurity drop. That is, whatever, let us say parent impurity was 0.9 and child impurity I got in one case 0.2 and in another case 0.3. So maximum drop would be in case of 0.2, right? So I selected that theta value which gave my impurity as 0.2. So this division we we did not need to do, because when this XLB minus maximum QLB you are doing, then you get the maximum value. You don't need to divide that. So we avoided this division. This division was not there. Without this division also, you can proceed with the impurity calculations. But if you implement a divisor, means division, then it will increase the resource consumption. So this was my overall architecture. Here I had 3 types of nodes: mean dependent, axis aligned, and leaf node. So based on the depth, DMD till DMD, I had mean dependent nodes. Those were all done by calculated from my training data in Python. After that only I implemented on hardware. So after, if depth is less than DMD, then we have to process the data in mean dependent node module. More than DMD and less than Dmax means it is an axis aligned node, and if it is in Dmax means last depth, it is a leaf node. So here then we used a multiplexer to select the node number. We got to know that it is mean dependent node, but what is the node number that this data is going into? So this multiplexer is used for that. So in memory also, I used some circuitry to speed up the memory access. So now I have here mean dependent circuitry as previous to the same to the mean dependent node, and this is my axis aligned node circuitry. Here what we are doing is we are taking a comparator and an OR gate. So if my comparator means previous data and new data I am comparing. If my previous data, new data is greater than previous data, then means R max needs to be substituted. If my new incoming data is less than the R mean, that is been taken from the previous incoming data. So if it is less than R mean, means R mean is not my lower limit. I have to store this new data as the R mean. So this comparator was used for that purpose. And then two multiplexers were used, whether the data needs to be updated or not. Based on that, in the update module, theta and dimension was updated. After that, in the final step, theta and dimensions across theta across all dimensions were compared, and whichever was the let us say I have m features, right? So this m such modules were used in parallel so that I can compare the theta for each dimension in parallel. So once I obtain the theta along jth dimension, then j plus 1 and j plus 2 are also ready at the same time. So I am again sending it to this module where all the thetas impurities are calculated, and those impurities across all dimensions are compared. Whichever impurity is less across all dimension, that theta is stored in our memory, and that dimension is also stored in our memory as j. So this comparator was also pipelined to further speed up the operation. So in comparison, we know that in digital, the bits can be either, if two numbers are there, A and B, the bits can be either 0, 1, 1, 0, or 1, 1, or 0, 0, right? In case of 0, 0, or 1, 1, the LSB, if it is MSB, if it is equal, then we go for next bit. We compare the next bit. If next bit also equal, we compare the next bit. If all the bits are equal, means my number is equal. So I used XNOR gate for that, and for combining all the bits result, I used this AND gate, and this multiplexer was used to choose between whether it is greater than or equal to, or it is less than. For greater than, it was output was 0, and for less than equal to, the output was 1. So this delay was inserted for to improve the pipeline critical path, to reduce the critical path, because the critical path is the time between input to the register or input to the output. So if I implement a register in between, then the time between input to the register will be my critical path, will be reduced. Otherwise, this whole thing would have been my critical path, and it would have reduced my operating frequency. So here my frequency was improved to a high level, because inside this modules also I have used pipelining this time. So my speed was increased to 200 megahertz, and in the same board using this Verilog HDL. So now I have tested it on 5 different data sets. This memography and occupancy are from the previous one, and now activity recognition, whether you are running or you are sitting, you are standing or you are walking, those data set also I inculcated this time, and I got good results as compared to the mean dependent nodes. This mean dependent node means TMDT, what TMDT would have given. Based on that, TMDT took less time, but accuracy was less. My hybrid ones took more time, but accuracy was improved. Accuracy has improved as compared to the previous algorithms. This is latency comparison with the card hardware, and this is my resource consumption. So I also proposed on perceptron hardware, that is neuron hardware, using sigmoid and offset binary calculation. So I won't go into the details of offset binary coding. In this offset binary coding, what happens is, if you are storing one data in memory and you are another data is you are giving as input, then you don't need to do the multiplication. You can just do shifting and addition, and you can realize the multiplication, either floating point or fixed point. So that was one pros of this using offset binary coding, because then I completely removed the multiplication need in the neuron. And then I used sigmoid activation unit. There I used Cordic algorithm, that is coordinate rotation coordinate rotation digital computer. So these were the equations involved in offset binary coding, where you have a lookup table of one value and another value that is the weights are already fixed, right? You can store them as lookup tables, and the incoming data you can give as this xj, so it would compute your inner product without use of any multiplication. So this was my lookup table, how the data was stored, because we have only 2 bits, 0 or 1. So either it will be negative or it will be positive. So based on that, so this was my architecture. In Cordic module, we have two types of Cordic calculation. One is rotational axis Cordic calculation, and one is VLC. So what happens is, if you need exponential or cos type of calculation, then you can use rotational axis Cordic, that is RLC. Or if you want to just calculate e power 1 by e power x or 1 by y like that, those values can be calculated using VLC Cordic. So what I did was, e power x I calculated using RLC, and sigmoid is 1 by 1 plus e power minus x, right? So e power minus x was calculated using VLC module, and then by doing it one inverse of that, I got 1 by 1 plus e power minus x, that is my sigmoid calculation. So this is the Cordic. In this range, I operated the Cordic. If it is in this range or that range, then you can directly get the value, right? You don't need Cordic there. This is 0, and that side it is 1. We can implement the 10H also using this Cordic architecture. Cordic is basically, it calculates the angle using iterative analysis type of thing. So that is the basic idea between Cordic. So this idea was taken from actually a mathematician. I forgot his name currently. From his idea, this Cordic architecture actually came. So I pipelined the already existing Cordic architecture to make the execution even faster. So this was my oblique decision tree that I'm working on now. So here we have neurons in one unit, one node. So according to my sigmoid, it is either if it is greater than 0, it is sent to left, or if it is less than 0, it is sent to right child, like that. So in this case, as the complexity is increased to some extent, so here I am getting good results for this cryotherapy also. This is a very small data set. I think around 60 to 90 instances are there. So here also I got good accuracy, which did not give any accuracy for the other two algorithms. So I tested on this 8 data sets and this algorithm. Then it was the classification was implemented for this biomedical datasets. So the Python and FPGA I have compared. Accuracy, there is a small gap, but in the latency, you can see that the latency is highly improved. So this was my last publication. And now one is under review of training of this neural tree for biomedical applications, basically. So this I have compared my classification accelerator with the existing ones. My throughput is a little less because I'm going for biomedical applications. I wanted it to be resource efficient. So in my case, the resource is lowest, though more than this one, but this throughput is more than this. So I have hit a trade-off between this resource and this timing. So this I already told that it reduces the latency, and training implementation enables the hardware reuse for various applications. It is not confined to one application. And I'm also working on random forest, neural forest implementation, training, classification, both. So what I am doing is I'm first testing my algorithm on Python, how it is performing. Based on that, then I'm coming with that algorithm to for my hardware implementation. So my basic bottom line is that I have to reduce the complexity, as the computation resources are limited on my FPGA or ASIC. ASIC, it is even more limited. So these are my publications, and these two are after my PhD. So and this is still in early access. And another one is, these are my conference publications. This was with my student from SRM. Others are from my PhD. And another work, these are my references. Another work is under review in T-Biogas currently, that is for biomedical circuits and systems. So the references are old because this is from my PhD work. Yeah, thank you. Thank you. Any questions? Latency. You have the critical path, right? After you did the implementation on FPGA, you will get a maximum frequency. From there, then I'm going back to the simulation. After implementation, you can check the simulation. So when you're training, I have a once output signal training done. When up to that, starting from the reset till training done, I'm counting the clock cycles. And multiplying with that time period, I'm getting my latency. Understood?
Before you deploy the model on the FPGA, we have to quantize the weights a little bit. So what kind of quantization are you doing for, say, the perceptron model? We'll have to quantize those weights, right?
Weights quantizations. I am not quantizing the weights here because I'm taking fixed point, and this weights I'm storing in a lookup table, right? So lookup table, let us say 0.49. So all the values are normalized between 0 to 1. So 0.49, 0.3, like that. So whatever after decimal is there, I am storing that only in my lookup table, right? So I don't have to quantize.
Also, in one of your literature surveys, they are using this ensemble method called XGBoost. So in your implementation, have you tried any ensemble method? Because that will help you in your
XGBoost, yeah, because but there are the calculation complexity is more, right? That's why I have not implemented those algorithms till now. I have worked on CNN classification implementation, but this decision tree classification I am not implementing.
Yeah, so if you compare with the 100x and 114x, if you do HDL synthesis, how much does it speed up?
Mine case.
Yeah.
This is 100x. That these are classification, right? So I have compared in my last
But this is also implemented in the hardware, right? So you write the program in C and it's synthesized in FPGA.
They have implemented only the classification. I have implemented the training.
Okay.
That's why I only kept this to show what are the works done on decision.
But if you write the training algorithm in C and you synthesize it on FPGA, what is increase in speed up compared to?
They are using high level synthesis. They are directly taking this C.
Yeah. So if you go in that approach, if you compare that with the HDL based synthesis,
I'm getting a higher speed up. I will show you with this Chrysos. He also did this thing, high level synthesis, due to which he required 5 FPGAs. Here it is not there in this design. See, this is my most simple design, TMDT serial one. This was my first design. So here you can see the latency speed up. He needed 260 millisecond and I needed only 0.49.
But is it the same algorithm?
Yeah, algorithm is different. I have only taken for same. That's what I'm saying. That's why I reduced the complexity of the decision tree. I could not do this conventional DT because
no, it's the same algorithm that there is a TMDT algorithm. If you implement
still,
it in
still
C,
FPGA will give you higher.
But how much? What percentage? 50%, something like
that. In the classification, I have compared it with this So I think it would be there. So here my throughput is less, I think, because I used some resource. These were biomedical applications. Here I don't require speed. So here I got less throughput. I did not go for the, means I can do more modifications in the architecture. Then I think speed up will be more in case of FPGA. It should be. By how much, I am not having any idea right now.
Across done so many implementations, right? Different implementations. So how is the power consumption?
Power consumption for my designs. See, I am doing.
Now, if you did you compare means with the improvement of your accuracy and all the stuff, how is the power consumption improving?
Means with the other works.
Yeah, or maybe in your work itself. How?
So my work, the power consumption for one design, it was less. I implemented on RTX 7 also, because during my PhD they asked implement on same board and what is the result. Then RTX 7 above 3 and my one, from one design my power is less, but for other two it all depends on your architecture and what you want to trade off. As it was a biomedical one, so I trade off this speed to some extent, but still I used some pipelining inside comparator and those things, which resulted in this higher power usage.
What are the, for example, when you implemented those multiple feature based, like you use extra FPGA.
No, extra FPGA I have not used, only one FPGA.
No, I mean the working part of it. It would have consume additional power. So in that respect, it's for the number of features when you increase.
Yeah, number of features, if I increased, yeah, the power will increase, because I am doing in parallel for all the features. So more comparators, more multiplexers. Okay, so but 2-3 features, if you I have tested for, I think 6-7 maximum. So if you go till 12 also, there will not be much higher power. But if you go for 32-64 features, then your power will increase, because there are only small comparators and or gates there, right?
Okay, so let's thank Dr. Rituparna again for the nice talk. Thank you all for attending, and hope to see you in the next talk also. Thanks.